Yes. And then I want to hide this stuff. Yes. Right. Knowledge representation and reasoning. So yesterday it was, well, I gave an introductory class, really starting from far away. So kind of talking about AI and the and the challenge of symbolic versus connectionist way to implement intelligent functionality. I am today I have two items on the menu. First, I want to converge really to or narrow down the practical part of the course. So we will be talking about technical systems where reasoning is needed. So and I want to give you some extra motivation why it is needed and why we cannot achieve it with conventional approaches to creating software or programming. And then today we also start talking about definitions of logic and reasoning. So the formalism behind it. And so this part will continue even next time, where we will be talking about propositional logic. Yes. So what is the technical scenario that we are considering? And it is actually funny, or funny, maybe not very funny, but and I'm using fact. I'm this morning. I was working on a proposal, on a research proposal for creating global scale knowledge models or models, world models. Sorry, to correctly say. So world models, and I was actually thinking about this kind of scenario. So we are already in 2023. We live in this situation where we are surrounded by computing devices with different computational capabilities. Large, stationary computers, laptops, mobile phones, embedded devices. Embedded devices could be static versus mobile. Plus, we. Can you please mute yourself in Zoom? Thank you. Maybe I can. Sometimes missing. It should be in participants. There's a button on your phone. Yeah. You made it further down. This one. You should, by the way, help me out with the navigating on the screen. So I have some issues recently. You too. Yes. Okay. Thank you. Okay. Where I have been. No, that's a different thing. Yeah. Yes. But well, all these devices, so they produce tons of digital information, and so we are exposed to this digital information through a variety of services, and everything already now is interconnected. So whether you book a travel, with Google Flights or whatever, or you I don't know, do some financial business with your bank or anything else. So there is a great deal of communications involved between different services. So and all in all, so such systems. So in this case, in this context, we are talking about networked applications, which interconnect heterogeneous components. And in these settings, these heterogeneous components, in order to deliver some useful services, they demand integration, interoperability, and collaboration. So this needs to be said loud. So these are the key elements. And once again, so examples of such applications, there are many. So I named just few examples on kind of, I mean, from the personal individual perspective, but in general, businesses are highly digitalized nowadays, and decision-making processes and there are of this kind of heterogeneous character involving interoperability of many services. Groupware, whenever you schedule something, that's another type of application that requires collection of heterogeneous and processing of heterogeneous information in order to kind of find the common denominator when, for example, scheduling an appointment or so. An application very so to say, or closer to the main business of this university, like intelligent industries. So the concept of Industry 4.0 assumes smart devices. So compared to traditional industries, which still are use hard-coded programs. In the industry of the future, so all components involving in production of something supposed to interact with each other. Why is that so? This is to deliver flexibility in, for example, a reorganization of an assembly line. Or a manufacturing line on a floor. You can think about scenarios, and in this context, we are still only in the very beginning of the process. You may think about replacing certain components, certain machinery with a new type, and this machinery should possess self-configurability properties. It means that it needs to understand the context of what is going on around it and choose the best configuration. Another thing is retasking. So if you, for example, have production of certain items, you want to very quickly adapt your production line to produce something else. So the entire distributed automation system should be reconfigured smoothly to streamline this process. The web, so that's another type of the technology which demands intelligence. So whenever we think about software, so now we think about software that extracts certain information for us, not knowledge, but information. So it needs to kind of understand the context, so how to deliver the result which satisfies your request. So all in all, we are talking in all these cases, we are talking about ubiquitous computing systems, and this is again, this is rather different from the yes, please.
What does ubiquitous mean?
Ubiquitous means that it exists. It's kind of ambiently existing, so it exists everywhere.
Okay.
And takes into account takes into account variety of heterogeneous information.
Okay.
So, but the properties is that such systems they exhibit autonomy. So you do not program exact set of actions, but rather a system adapts its functionality depending on the environment. So, and there is a need to obviously characterize the environment for these purposes. And the challenge here is that the environment in many cases is dynamically changing. And properties of objects, they also change with time. And such computing systems, as referred to here as ubiquitous, they need to adapt to changes. By the way, so what do I mean by changing set of the set of properties? So let me see. There is a. Can you read loud, please? So it's just too small. Anybody?
Is heterogeneous data the same as unstructured data?
Which one?
Is heterogeneous data the same?
No, heterogeneous here means that it's not necessarily unstructured. The data can be structured, but this is data of different types. And the number of types in such systems is large, and the system should be able to operate with types which are maybe not known at the time of its creation. Yeah, so I was commenting on the fact that properties of objects on which such systems operate, they change with time. So there is a kind of intuitive analogy here. So if you consider a set of properties characterizing a human being, so they transform. So we have different properties when, for example, we are small children, so go to like preschool children, then our set of properties change quite substantially when we start going to the school, and then yet another transformation of properties with appearance of new types characterizing a person. They come into place when you go to university and so on and so forth. So and this system again, so you cannot in advance think through all of this transformation. So this computing system, so following this paradigm, should adapt to this constant change in the environment and the object properties within this environment. Yeah, and that's what, and this falls under the definition of open system. So compared to traditional software, which is obviously a closed system, so which hardly coded, and all the facts are embedded at the design stage. So let's, yeah, maybe before showing this slide. So if we would approach creating an open system or designing an open system, again, that possesses these properties. So it is operating in the environment, so it's context dependent. So how would we approach developing such system? So why, for example, or can we adopt the traditional way of creating programs for that? And what is the traditional way of designing software in the first place? So when you write a program, so how can you describe this process? So what are the kind of necessary steps? So you have a specific problem in the first place, yes, to solve. And huh?
You don't apply the program, the problem cannot derivate from the original problem by much.
Exactly. And then you, yeah, but if you start kind of continue from the beginning, so you have a concrete problem to solve, and so what you do, you first analyze this problem, and you use your expert opinion to characterize this problem through certain data structures. So you design data structures that are needed to solve this particular problem. And these data structures, they are handcrafted facts about a specific instance of environment that for which you create a program, right? And the problem here is that your processing is tightly bound to this to the facts that you use in form of data structures. So this is the current, this is the traditional software development cycle. So you have data and you have set of instructions. So if you change, if you want to adapt to changes in the environment, so you obviously need to change the facts about your system. And changing the facts means that in most of the cases, lead to the change of the execution flow. So the flow of instructions that that you implement. So, and that brings us to the main kind of feature that is that traditional software development is lacking. So is the mechanism for deriving facts from other facts and incorporating them into the functionality of the program. And this capability of deriving facts from other facts is, in other words, called inference. So what we want essentially, so if we talk about this, if we want to create an open system that kind of assumes that there will be changes in the environment, and we will now also talk about different environments, or what kind of changes it can be. Then we basically want to separate the representation of facts, so the way how we represent the facts, from the procedures or from the way how we process these facts. So we want to decouple this two things. And that would be in the main paradigm in intelligent systems. And again, so the overall goal with this we want to achieve is to increase system autonomy. So that the system, by deriving facts from other facts, is able to adapt to changes in the environment, and it means that the system becomes more autonomous. And obviously, we are talking about heterogeneous, again, different scenarios. We don't need full autonomy. So there are scenarios where we don't probably need autonomy. So we just need sequence of actions. In other scenarios where we, for example, want to exclude human from the loop, then we need quite high autonomy. Like, I don't know. I mean, a good example is zero human vision in mines here in the north. So how to automate mines such that no humans operate in dangerous environments. And so this also changes the way how you approach the programming. So your program doesn't have a kind of a predefined sequence of actions to solve something, but rather you set a goal and your system attempts to achieve it. And in this case, well, let me skip this kind of not spend too much time on this textual slide, but we need another approach, and this approach is not new. So that it is existing for quite long time now. It is called agent-oriented software engineering. By the way, so if I may ask, in your previous studies, did you encounter any agent-based programming? Anything? Can you give me examples, like down to, I mean, in the current technology where agent-based approach is used? I mean, for creating software.
I mean, I read in the book, and it says that a procedure can be defined as an agent, kind of.
Mm.
And if you know that there are multiple procedures, you can have like the output of one could be the input of another agent.
Yeah.
But I don't know, like
but can you give examples from modern world technology where this approach is largely used? Huh? Self-driving cars. Self-driving cars. I don't dare to say. I don't really know how they they implement it.
I'm not sure, but I think Amazon's work storehouses where they have automated robots to store all the
What about games? So programming games. Did you try programming in Unreal Engine or?
Yeah, I did with Minesweeper.
Yeah, so I mean, I mean, this approach is, as I said, it's not new. So then the question is, how intelligent this agent is that you create. But the modular piece of code that does something and then also communicate, it takes into account input from other similar entities to achieve certain goal. So that this approach exists in development of modern software. Yes.
Maybe you said that assembly line is could be like multiple agents.
Absolutely. Absolutely. And by the way, so that's thank you. So it's kind of reminded me one thing. You may expect a guest lecture by my colleague from industrial automation side of our group, who will be talking about multi-agent approach to electrical grids, so energy systems. So it's really down to earth application. So not very much super intelligent, but application of multi-agent systems to optimization of energy distribution. So that will come later on. And again, so agents, very quickly, just to give you some broad perspective, so they can be different kind. So there's some agents, they may assume they may assume certain functionality as a reaction to certain input. So reactive agents. So then interactivity. So while some agents may rely on pure kind of locally available information or direct sampling of the environment, in other cases, so this decision making process involved communication with other agents. And in this case, for example, this travel planning. So this is a good example of such functionality where you need to ask from many service providers to find a kind of best price. Yes, well, the slides will be published, so you can read about these definitions offline. What I want to say is, so I want to probably comment more about the environment. And how it affects creation of agents functionality. So environment in its turn, it can be classified as along different categories or axes. So accessible versus inaccessible, deterministic, non-deterministic, episodic, non-episodic, static, dynamic. So in all these cases, so depending on in which environment, for which environment you create an agent, it becomes more or less complex task. So accessibility of the environment means an ability for an agent to obtain accurate information. So most of the environments are not fully accessible. So and in such environments, it is obviously harder to create an agent. Deterministic versus non-deterministic environment. So the environments which are more predictable. So obviously, I mean, you can, I mean, the agent's behavior is simpler to construct, where compared to the case with the uncertain environment. So where it is changing. Yes.
In the book, it says like that the stochastic process could be non-deterministic.
Mm-hmm.
Is there a non-deterministic environments that are not statistic?
Stochastic. I'm just thinking. Well, stochastic here means so introduction of probabilities of events that happen. So no, non-determinism is connected to probabilistic nature of events. Because otherwise, I mean, by definition, it becomes deterministic. Episodic, non-episodic, that's again intuitively easy to understand, and non-episodic is the most troublesome. So when it's an environment in which you cannot kind of spot global patterns, and so in this case, so you need to assume you cannot assume that certain actions will repeat, and such behavior is much more difficult to create. And static versus dynamic, so that's concerning the time, whether the environment changes its properties with time or not. So that connects to, again, to the amount of information that is needed to describe certain scenario. For the static case, you most likely have a finite set. I mean, you can describe it through a finite set of variables. While for the dynamic environment, it's you need other solutions. Right, and so in all these environments, so we need to somehow we need to have a development environment which allows to produce software in a unified way, and basically abstracting away from the from really the specifics of particular environment. So you really want to focus on high level functionality of the agent. So that's again one of the major paradigm shifts compared to the traditional way of creating and to do that, so you need changes in the execution environment. So purely talking about the development. So so you need to support. So you can think about these different agents as pieces of code that concurrently running. That are concurrently running on specific computing platform. And this piece of code is only there is an interface that abstracts away the all the complexity of underlying computation and communication model. So to give you an example, so in the low-level programming, like if you want to create a networking application, so what so you typically use sockets, right? So you have an application in mind, and so you develop you develop both the functionality, and then you also kind of need to be aware about the communication channel. Here, you need a kind of middleware system that hides away the complexity, the underlying complexity, focusing only on high-level interactions between agents. So let me just see if I have a better slide. Yeah, and there are different, again, so this information this slide and a couple of previous slides, it is mainly for information. So if you want to start developing agents or intelligent agents functionality, then most likely you will come across the need for choosing a framework, appropriate framework. And this framework, as I told you, so it delivers you a capability of just focusing on the development of the agent, taking care of all the communication primitives, or hiding away the communication part. So some of the examples of such systems are listed here. So maybe the free of charge Java-based, which I use myself, is Jade. So I think it's a platform, but there are also others that you can consider trying out. And here is the link where you can read more about available information. So in this domain, there is a great deal of practical information on how to design agents as I mean, from the programming perspective. So there are again, just to give you some insight information. So you there are standards describing the way how you format the messages to be exchanged between agents, so that all agents can process them in a unified manner. But then what you place inside, so the functionality that you place inside, that's of course up to a particular programmer. So when talking about the main difference of designing open systems or developing open systems compared to traditional systems, I was talking about a mechanism of deriving facts from other facts. And well, I used word inference. I mean, here you can interchangeably also probably use word learning. So you learn the new facts. So what is learning in this context? What kind of learning we may have in general? So yeah, the main idea is that we want to basically account for the new information that a system encounters at a given time. And there are different ways on how we can process this information, this new information. One naive way, of course, is memorization. And this, well, it's a valid method for learning, but again, so in the context of global systems, so at least this is inefficient, simply because the number of facts and relationship between different facts are way too large compared to the physical capabilities to store and efficiently search the information. What is more important is to be able to derive rules, like general rules according to which the outside world exists, and build your program on top of these rules. And here again, so why not then to memorize rules? Yeah, that's a good question, because that is how, for example, classical expert systems are built on. So they are built on as a collection of rules. So the rules are constructed by experts. So they collected in very large knowledge bases, and then so the inference or deriving facts from other facts basically boils down to navigation through this set of rules. However, in general case, and well, even in the expert system case, it's very difficult to come up with extensive set of rules. So you need something more flexible. And that's what we will see on the case of ontologies or ontological descriptions. And as soon as you give a possibility to existence of such new rules that appear over time, so then the problem of creating, processing of these rules start to be more complicated. Right. So recapitulating the previously said facts, so what we want to achieve with intelligent systems or agent-based system is to decouple the knowledge representation and the processing that is in inference. So what is inference? Okay, so you maybe explanate a little bit, but so what does it mean? So what kind of inference it can be? So this deriving facts from new facts. So what concrete instances of such process you might think about?
You also have that in statistics, right? Third.
Statistical inference. Yes, if you want to spot certain patterns appearing, frequently appearing over time or in different contexts, yes. It's I think it's I'm not sure to which passage you refer. I mean, to me, it's more of a kind of generalization nature. Or
what I understood is like when you're trying to find the parameters of certain distributions and stuff.
and that describe certain data.
Yeah.
Still, then to me, it's more of kind of I mean, as building a model of specific phenomenon. So you when you and then so this model in itself becomes a description of this phenomenon. Well, I guess one can classify it as an inference to some extent. But what I rather mean is here. So so when at least in the context of that's what you say. So that makes sense more in the context of learning representations. So in this case, inference means so for example, to find to give an index to give an input to find a correspondence of a specific category. So but in the context of symbolic reasoning, so we are talking about deriving facts from facts. And so one of the valid reasoning tasks would be making explicit information implicit. So what do I mean? So this specific type of reasoning is very typical to semantic web. So where the information about certain fact that's for example, a person belongs to a person is characterized by through a set of properties, but some property is missing. And then in a given context, through a set of existing rules, you may make this fact, this property, you may fill in this missing value with a specific content, and this is a kind of valid reasoning task. So reasoning by default, so it's is to understand a fact because of the lack of contradiction. So if there is nothing that contradicts certain fact, then you can you may assume that certain fact is valid in the system. And there are other other types of reasoning, so they all kind of, you will do it as part of reading assignments in the book. So I guess now it's time to make a short break. So we do 5 minutes leg stretching.
You say that solving like a Sudoku puzzle.
Mhm.
Is this the same type of reasoning
Absolutely.
with the inference? Or is that too simple?
No, absolutely. That would be. I mean, you can formalize it as a reasoning task.
By looking, oh, it can't be 3.
Yeah, exactly. So actually, that's what we. I mean, that is pretty much similar to what we will be talking about now. So I mean, in this case, very simple logic. I mean, the simplest logic is sufficient for solving this task, like propositional logic.
Yes. Ja, men jag bor alltså, det spelar inte dig någon roll. De spelar inte pengar på det. Det är lite svårt. Du måste ju även prata med dig. Men tänk på att jag som tänker att jag kommer med min fråga för att skriva in det kommer till lektionen eller
All right, so let me start sharing the screen again. So let me see. Yes. All right. So let's start talking about reasoning more practically, so to say. So first some definitions. So in order to kind of formalize the reasoning process and apply, well, one or another logic, so we need to introduce certain formalism here. And so to begin with, so recall this illustration of an agent. So again, our beautiful agent with sensory system. So or perception system through which it senses the monitors the environment. And so we need to characterize this somehow. So basically, so each and every percept, we need to assign a certain symbol, well, a variable. And so we are talking about a system of sensors that an agent possesses. And again, sensors, it's a generic term here. So in the context of a robot, so these are real sensors. In the concept of software agents, so these are some input interfaces through which it receives some information. But nevertheless, so we want to characterize them, and so we assign a symbol to each of the sensor, and collectively we characterize our perception system through a vector of symbols. And yes. So for example, well, the specific vector is kind of detached from a particular example, but what we can say that in this case we are talking about an agent with 4+ sensors sensing different characteristics. Maybe one of them is temperature, and
I want to ask about sensors.
yeah.
Are there kind of sensors that they use actually to learn problem in their core system? For example, take some radiation, something like that, and if something is off, to tell that this is an anomaly.
Yeah.
But not to analyze it, to take raw data. But to have a pre-installed software ML programs inside them.
Exactly. I mean, that's totally correct understanding. Here, so that's what you are talking about here is really the transition from sensors to symbols. So which is called, which corresponds to the symbol grounding process. So we, so in intelligent agent-based systems, so there is a block, so software block, which directly interface the physical sensors, so which produce raw data, and these blocks normally has some processing. So not always learning. You don't need learning all the time to characterize the input. So it can be classical methods from signal processing, which tells that a certain action happened on the sensor. So this is kind of interesting and pretty much important. So not in all contexts you need to learn something unless it is needed.
Like that also happens in new age experiments.
In where?
In newer kind of new experiments happen in scientific fields.
Mm-hmm.
I'm 100% sure that can happen in optoelectronic experiments for counting energy, because we had to find ways to count the energy from a being that we couldn't otherwise.
Yeah. I can give you the following example. So, well, I mean, the domains can be different, and examples can be also quite diverse. But I mean, there are modalities. So here we talk about sensing modalities, which require learning of characteristics. So I call it features. And other modalities are simpler, and they probably maybe what is needed really is a binary indication that certain action have happened on specific sensor. So for example, we had this project about passive detection of cars. So a long time ago, so we had the smart sensors that we placed on, which we glue on the asphalt. And these sensors, these devices, so they contained microprocessing board equipped with two sensors. One is accelerometer, so like in telephones, 3 axis accelerometer, and another one is magnetometer. But and again, for the task that we needed, so we only needed to detect the passage of a car, and we needed to detect a type of a car. To do that, I mean, just to detect the event of passage, so that something exists. So you can do it with very classical method of, for example, finding a signal envelope and measuring the floor level, and then measuring the deviation from the floor level. So as soon as your signal goes up beyond certain threshold, so you kind of set a flag. Okay, so there was a passage. But the same sensor, physical sensor, can result in a different symbolic sensor, for example, which tells what kind of car has passed. And for that, you would need a certain learning, so a certain extra processing. So it's not only the deviation of a signal from some ground level that is important, but also its shape. So basically its signature. So which is different for say passenger cars, trucks, buses. So this would be an example where one physical sensor would require different encoding engine or transformation engine to really the symbolic representation. And that's in the scope of this course, we are focusing on this final step. So we assume that these mechanisms of processing of raw data are in place for our needs, and we can focus on just final outcome of these blocks, which are described through symbols and vectors of symbols. So, and in this case, again, so this placeholders which show none in this example, they could be, so one of them could be like, so there was a car, and the second one, there was a bus, etc. So, so the idea is that you assign symbols to different symbols, sensor modalities. Yeah, and then as soon as you kind of have an understanding, so how many variables you have that describe your perception system, then you immediately can think about all different combinations of the values for each of these variables. And one specific, and sorry, oof. And one specific outcome of sensors. So sensor one reports this value, sensor two reports this value, etc., etc. So, some sensors don't report anything. So this combination, they characterize a state of the agent at a given instance in time. And then basically the way how we move from one state to another state is described in logic by a so-called transition model. So basically, action of changing one state to another state is the transition model of the action. And obviously, so we are talking about the case where only few transitions are known at some initial step, or maybe none. So you start you place an agent in an environment, and it starts from scratch. So it has current state, but it doesn't have any previous history of state changes. And that's what we want to do. So we want, so the task of agent is to discover this. Yes.
How do you define state?
How do you find, or how do you define? The state is the collection, is the particular instance of your percept vector. In this case.
Percept vector.
Yes.
What's that?
So okay, once again, so we have a system. So it is equipped with sensors. All sensors together constitute percept system, right? So this is the system through which agents perceives the world, the environment. And we talk about, so we assign a symbol to each of the sensors. And collectively, so this percept system can be described through a vector of symbols. So basically, I mean, just a set of, a list of sensors. And then you start to, yes. Huh? Symbols and not numbers.
And also, all these have anything to do with the symbol combining the business.
The last thing I didn't hear.
Also, that's the symbolic connection between features.
No, here you see we need a machinery that allows us to do formal reasoning, to formalize the reasoning process. So in the same way, how programming language, like any programming language, take Java or something, is a formalism for writing a software. So we need a special language, a special formalism to express situations, the transitions between situations, and derivation of the facts. That is why, so I mean, so we characterize, so we assign symbols to, so we need symbols. So you think about this symbols as variables that take certain values. And values, again, in the simplest case, in the simplest logic, so they are of binary type. So either this symbol is on or off, true or false. It is somewhat simplified, but so that's what you say is a kind of more complex thing. So when you let each variable to have a range of values, so you in this case you're talking about different types of logic. Yes. So and in this case, the goal of this reasoning process inside the agent is really to complete the transition model. So so how one state transits to another state, and use this information to maybe reason about what to expect in the next on the next transition. So these rules will be will assist you to in taking a decision on the next step. So let's now introduce some more stuff into it. So we want to describe a situation. So we with the help of our percept and facts. So and this is the example you will be working with in Lab 1, or somewhat simplified example from Lab 1. So in Lab 1, you will be working with the Wumpus world, which is quite interesting. So basically creating the reasoning engine for it. So here is kind of soft introduction to it and to propositional logic. So here is the scenario. So this is our little world, or a little scenario. So we have 1, 2, 3, 4, 5 cells. So cells or rooms. So we can we give a name to each room, so, or we actually refer to each room through the corresponding coordinates, ij. And then, so we have, we consider the simple situation where we have certain entity placed in the cell, or poison in this case. And if poison is placed in a cell, then in the directly adjacent cell, you will perceive it through your sensory system. So again, so referring to this Wumpus world, so it will smell badly. Well, there it's instead of poisonous, I think it's Wumpus who smells bad. But you're with me here, right? So so this is a situation. So we formalized our physical environment, so through giving a name to different places, physical locations, and then we also well, actually, this information we need only to assist us with the definitions. The only important information in this scenario is that is exactly this sentence that we can understand that something is located, which is not directly observable through through the current observation in the cell. But yeah,
what is the condition? Like how do you know that there's poison adjacent?
No, this is the initial assumption. So this is something given to you.
Mm-hmm.
So if there is a poison in certain location, then in the directly adjacent cell or room, you will smell it.
But why don't there is poison in square 1, 1?
Well, yeah, that's a good question. So I mean, so you need to place yourself somewhere.
Okay.
So and this is your initial state. Okay. So basically, where your transition model is totally blank, so you don't know anything.
And there is no poison there.
And there is no poison there, and there is nothing in there. Yes. Yeah. So we will be talking about situations and in the so just to stick to the terminology of the book, so a situation is a possible world. So a kind of outcome, or a possible outcome of a specific event. And so the possible outcomes, so in our case, would be like a poison is located in one of these three rooms. So let us first trace this example graphically, so without introducing the predicates and such. So once again, so we give a symbol, B to our percept, and give a symbol P to the fact that it is poison somewhere. And one possible world, a possible situation would be that I transition to this cell. So 2-1. So I was here. I transition to this cell, and I smell bad smell. So basically, it smells bad. So what are the possible outcomes for this scenario? So either of these three cells can be either in true or false state with respect to availability of poison. So and the question is, so how many such situations we can have in principle? So in this case, so we have three cells, 2 to the power of 3. So it's a binary example. So we have 8 possible outcomes. How the poison can be located. And basically we will, yes.
Is M4 really possible, because if there's nothing there, do you really smell?
It is possible in a way. Well, that yeah. That's you see, if you carefully read the title here, so these are possible worlds, even with respect, even what is it? Do we have? No, it's let me think about it. Well, as a possibility, if it is a feasible.
I mean, could it smell bad without being poisoned there? Like, that's the question, right? Like, could it just be smelling bad because
Something else. No, I mean, well, here we are talking about. I mean, so this situation is a feasible outcome, maybe without reference to bad smell. So it's all possible combinations of availability of poison in 3 cells. If you just can consider, if you disregard. You disregard the situation in this cell. But I have to. To me, it doesn't look very contradictory. So let me see. Let me try. Yeah. Yes. Yeah, I think that that is it. So here, so we are talking about a situation from the point of view of availability of certain thing in one of the three cells. Later on, we will make a statement. So we will describe a statement and incorporating the smell B. And in this case, this model will be excluded.
But doesn't it say like on the top, like where P is either in 1, 1, 2, 2, 1, 1, 3, like, and it's not in any one of them, so it shouldn't be included, right?
I guess it can be let's for a moment assume that it doesn't exist. So just for simple, and then you know, in the retrospective, we will see what is whether it's needed or not. So maybe it's safe to assume that this model 4 doesn't exist. Also, it is present on the slide. But again, so on the level of definition, so we have these models as possible outcomes of our situations, and so we can start making statements. So and a statement would exclude, so a certain statement would exclude some models from consideration. For example, so in statement 1, we say that there is no poison in cell 1, 2. So obviously, so we just account for all the cases which has it. And again, so let's forget for now about M4. So the same goes in a similar way. So we can construct a statement that there is no poison, for example, in cell 2, 2. So, and that would be another set of models that satisfy this this statement over here. And now, so we want to kind of extend. We want to extend the or enhance the situation. So now adding the availability of percept. So if we have a bad smell in a certain cell, then it smells nothing, for example, in cell 1, 1. So in this case, we will have this model. So no contradictory vision here, right? So it's quite logical. So I guess for now, so so next time, so we will start from this moment. So we will develop you know, a complete system for reasoning about situation. So here, I mean, we need to transition from this graphical representation, which is more kind of observational nature, to more formal description. So introducing syntax, adding semantics, and possibilities of reasoning with logical operations. So we start from this point. So that's all for now. And just as a final remark, I still don't think that I think I need to revise this statement here. Basically saying that in either yes, I think you're right, or none. So just to account for that case. So because it's not connected to the observation of this smell at this very moment. It just introduces the notion of model. I mean, all set of models. And then subset of models that describe certain statements. And all set of models is obviously, I mean, in this very example, so is about all possible combinations of 3 cells and possible values in them. Yes.
Yeah. Bara liksom. Ja, bara han. Så det är bara att
Jonas, ska man lägga till några fler punkter eller?
Som ni tycker är viktiga och intressanta för er, men de där är nej, det var så sagt. Ja, men då kan vi nog ja, så det är bara de ja, det är så för att fråga där. Då kollade jag på texten. Jag ville svara på det genom som möjligt innan jag började läsa. Så jag gick till 20:an och sen 9:an så hittade jag svaret till första. Och så blev jag lite förvirrad. Alltså, vilken del, för att jag har en 24.
Jo, men det är samma, jag googlar att det är samma.
Eller 24.
Nej, jag egentligen inte. Men det är
Alltså,
Och det är samma kapitel, det är 27, men jag sökte upp det och det är samma kapitel.
Ja.
Och där, men
För att jag hittade svaret till första frågan. Är det övning, är det skillnad? Difference between propositional logic and presuppositional. Jag bara,
men det är så flera ställen.
ja, jag läste det så vet jag.
Ja, det blir bra.
Håll en sån.
Jag har en fråga sen.
Ja, absolut.
Vad är tanken liksom att